Okay, let's just dive right in. We've been watching the global tech race for years now, and it's mostly been this slow, steady march.
A very deliberate pace.
Exactly. But what we've just seen, it's not a march. It's a sprint, a thunderous sprint.
That's a good way to put it.
We're looking at a really decisive strategic alliance between the UK and Germany. I mean, two of Europe's biggest industrial and scientific powers.
Formidable powers, for sure.
And it's all about the commercialization of quantum supercomputing.
Yeah.
This could genuinely be the defining tech gamble of the decade.
It's an acceleration that, we really haven't seen before in this specific field, and the political weight behind it is just, it's impossible to ignore.
Right.
So for this deep dive, we're looking at a recent Intelligence Digest that details this collaboration, and the timing is key. It was announced right at the end of the German president's state visit.
December 6th, 2025.
Yeah. Which tells you something. This wasn't some footnote in a trade deal. When you close out a major diplomatic visit with an announcement like this, it signals that the highest levels of government see this as a matter of core economic security.
Absolutely. Foundational, even. So our mission today is really to give you that shortcut, the deep dive into this strategic move. We need to unpack the goals they've set because they are incredibly ambitious. We need to analyze the funding, how specific it is, and, most importantly, figure out what this formalized partnership actually means for you.
For the enterprise decision maker.
Yes, for the person on the ground, anywhere in the world. Because this is so much more than just a news item. It's really a blueprint for understanding how these tech giants are trying to bridge that huge gap.
The gap between the lab and the market.
The chasm between fragile, complex lab research and, robust market-ready products.
And that bridge, especially in quantum, is just notoriously difficult to build. The information we're seeing suggests they're trying to solve the scaling problem, not through, isolated national efforts, but together on a unified front.
A united front.
Yeah. And by looking at the source, we get this immediate insight into their plan. They're aligning IP strategies, they're deploying very targeted funding, and they've defined three really clear product categories for the near term. It's an aggressive, very calculated move to secure a leadership position.
Okay, so let's ground this in context for a minute. The fact that this happened during the German president's state visit, why is that so significant?
Well, diplomacy at that level, a state visit, it's theater, but it's very focused theater.
Every minute is scripted.
Every single minute. So for the grand finale of that trip to be a technology partnership, it just elevates quantum from a scientific curiosity into a core piece of their bilateral national interests.
It's no longer just a research project.
Not at all. It signals a long-term binding commitment. I mean, state visits are designed to affirm relationships, of course, but they're also platforms for launching these huge multi-year initiatives that are meant to survive changes in government.
So it locks it in politically.
It locks it in. When you seal the agreement at that level, it basically guarantees that the funding streams and the bureaucratic streamlining, which is so essential for cross-border research, will be prioritized.
That makes sense.
It's the difference between, an agreement signed by a science minister versus an economic pact that's affirmed by heads of state. It tells industry and academia that this is secured by real political capital.
I found the source's description of it as a pivotal moment really interesting, but we need to go a bit deeper than just the phrase, what makes this concrete, not just symbolic.
That's the key question.
The source highlights this commitment to pooling their scientific resources. When two powers, like the UK and Germany, pool resources, what does that actually look like on the ground, in the quantum trenches?
That's the operational reality, isn't it? And in quantum, pooling resources is so much more than just merging budgets. It's about getting to critical mass in three very specific, very constrained areas.
Okay, what are they?
First is intellectual property, IP. They have to build a framework for shared ownership, for joint licensing, for protecting the patents that come out of this. And that is really hard when you're dealing with two different legal systems.
I can imagine. So what's the second?
The second is human capital. The global talent pool of, say, quantum engineers or algorithm specialists it's tiny.
It's very small.
Very small. So pooling means making sure that your top people can move seamlessly between a firm in London and a lab in Munich. You're optimizing the use of that extremely rare talent.
So it's about breaking down all those internal barriers that usually slow this kind of thing down.
Exactly. And the third piece, which might be the most technically important, is standardization and architecture.
What do you mean by that?
The quantum world right now, it doesn't have interoperability standards. The UK might have invested heavily in one type of architecture, say photonics or neutral atoms. Germany might be leaning more towards superconducting circuits or ion traps.
Different approaches to building equipment.
Totally different.
Yeah.
So pooling resources implies they are aligning their research strategy. They're deciding which horse to back jointly, or more likely, designing interfaces so these different national systems can actually talk to each other.
Wow.
That level of integrated planning is what makes it concrete. It requires real compromise and, the alignment of massive prior national investments.
And that alignment makes a ton of sense given the sheer scale of the technological hurdles they're facing. They're trying to unify their research strength to clear obstacles that maybe were too high for either one of them to clear alone.
It's an admission of the complexity. I mean, quantum development requires this immense specialized infrastructure. We're talking high-power lasers, deep cryogenic cooling systems, custom silicon fabs.
Incredibly expensive stuff.
Wildly expensive. And duplicating all of that in both countries is it's inefficient and it slows everything down. By pooling, they can use the best facilities each nation already has and then funnel their combined investment into new complementary centers. It's all about maximizing the velocity of innovation.
Now we have to frame this whole effort within its ultimate goal. The source says it's a direct effort to enhance economic growth and competitiveness on a global scale.
Right.
This isn't a passion project. This is a market capture strategy.
It absolutely is. And it puts this partnership right in the middle of a very intense global technological race. I mean, think about the scale of investment happening outside Europe.
The U.S., China.
The United States, with its national quantum initiative, major economies in Asia, especially China, they are pouring billions into establishing dominance. This UK-Germany collaboration is their answer. It's a unified attempt to create a European quantum champion that can set global standards and secure its own proprietary tech.
So the competitiveness angle really implies a race for, technological sovereignty?
That's the term, yes.
Because if they succeed in commercializing and scaling this first, they're not just creating jobs. They're securing control over the fundamental tools of future industries: finance, materials, infrastructure.
And being reliant on a foreign quantum provider in, say, the 2030s would be a massive geopolitical vulnerability.
A huge one.
Which is why there's this palpable sense of urgency. They aren't just aiming to coexist in the market. They're aiming for a position where UK-German quantum tech becomes the globally adopted platform.
The standard.
The standard. And that means getting a first-mover advantage, especially in setting the technical rules for things like error correction and quantum network connectivity. The strategic weight of this alliance is to ensure that economic dominance is the main KPI. It's as much about insulating their own industries from future foreign tech pressure as it is about creating new revenue.
Okay, so to sum up this first part, this is a deeply political, financially serious, and strategically unified effort. It's driven by a desire for tech sovereignty and global economic dominance. And it requires this incredibly complex integration of resources between two nations. That's a huge undertaking.
It's a monumental undertaking.
So that's the high-level strategy. But let's get down to the ground level. What does this mean for the engineers, for the physicists? What are they actually trying to fast-track here?
Right, the technology itself.
The core of it is quantum supercomputing. The source calls it a game changer because of its potential to solve complex problems exponentially faster than classical computers. And I really want to pause on that word, exponentially.
It's a whole ball game.
It really is.
Yeah.
Because that's the difference between just an improvement and a complete paradigm shift.
It's a profound shift. And for you listening, the key takeaway is that this is not just a faster version of the supercomputers we already have.
Not at all.
Our classical supercomputers, as amazing as they are, run on binary limits. Bits are a 0 or a 1. That's it. So if you want to solve a big optimization problem, you have to try the solutions one after the other sequentially.
Okay.
For simple problems, that's fine. But for really complex problems, the number of possibilities scales polynomially, which means the time you need just explodes as the problem gets bigger.
Can you give us a concrete example of that limitation?
Sure, think about the classic traveling salesman problem.
Right, finding the shortest route between a bunch of cities.
Exactly. If you have, say, 5 destinations, a classical computer can check all the possible routes in a flash. But if you increase that to 50 destinations, the number of routes becomes It's astronomical, roughly 50 factorial.
Which is a number I can't even comprehend.
Nobody can. Even the fastest supercomputer on Earth today would take longer than the age of the universe to check every single one of those routes. That's the ceiling. That's the classical computing wall we hit.
So polynomial scaling just means that once a problem gets complex enough, it's effectively impossible to solve.
It may as well be impossible, exactly. Now, you bring in quantum mechanics. Quantum computers use qubits, and these qubits can exist in a superposition of both 0 and 1 at the same time.
Okay.
And crucially, they use entanglement, where the state of one qubit is instantly linked to another, no matter how far apart they are. So think about those 50 destinations again. Instead of checking the routes one by one, a quantum computer, using superposition and entanglement, can explore potentially all of those routes simultaneously.
Okay, for those of us not deep into physics, can you just quickly unpack what entanglement actually lets the computer do?
It's a weird concept.
Mm-hmm.
Think of it like this. If classical computing is like flipping one coin after another, right, to see if it's heads or tails.
Okay, sequential.
Quantum computing is like flipping thousands of entangled coins all at the same time. And by looking at the outcome of just one of them, you instantly know the correlated state of all the others.
A kind of massive parallel processing.
Yeah. A massive parallel processing, that's what entanglement facilitates. And that is what gives you the exponential speed up. So instead of taking billions of years to solve that huge optimization problem, a stable quantum machine could potentially solve it in minutes.
And that's the game changer for industries like drug design.
Drug design, where simulating protein folds is currently impossible, or material science, where you could test the properties of molecules that don't even exist yet.
That kind of leap absolutely justifies this massive strategic investment, which brings us to the actual mission here.
Yeah.
Commercializing this exponential engine.
Right.
The partnership's goal is to bridge the gap between research and development and enterprise application. And as you said before, that bridge is a chasm.
It's a huge engineering chasm. The quantum advantage, it relies on maintaining these unbelievably fragile quantum states. That means isolating the qubits from everything, the environment.
So any disturbance ruins the calculation.
Any disturbance, a tiny vibration, a stray magnetic field, a little bit of heat that causes something called decoherence. It destroys the quantum state, and your whole computation is corrupted.
So we have this machine that can solve impossible problems, but right now it's stuck inside a super sensitive, multi-million-dollar lab, often kept colder than deep space.
Also in the deep space.
And commercialization means making that fragile tech robust, repeatable, and accessible.
Precisely. It's about moving beyond the cool proof-of-concept experiments and achieving what's called fault tolerance.
Okay.
Early quantum computers are noisy. They make a lot of errors. But enterprise applications, they demand stability. They demand reliable results every single time. So this UK-Germany funding is being funneled into things like error correction codes and specialized hardware, cryogenic engineering, complex vacuum systems that can keep those qubits stable outside of a perfect lab environment.
So for the listener thinking about this from a business angle, enterprise application really needs three things. First, scalability. You need enough stable qubits to handle real-world data, not just a tiny academic demo. Second, reliable accessibility. The system needs a robust software layer, APIs, programming languages, interfaces that allow people who are not quantum physicists to actually use it.
Like engineers, financial analysts.
Exactly.
And third,
integration. Enterprise application means the quantum result has to plug back into your existing classical IT systems, whether that's in the cloud or your company's ERP.
Right.
The funding we're seeing in the source is explicitly about fast-tracking that journey from laboratory innovation to market-ready solutions.
Fast tracking. That implies compressing what's normally a decade-long engineering phase into just a few years.
Yeah.
But doesn't that introduce a huge amount of risk?
It does.
I mean, if you're prioritizing speed to market, are you sacrificing long-term research or fault tolerance just to hit a political deadline? That is the critical tension in this alliance. It's a huge question. I think they're taking a very pragmatic approach. They're focusing on delivering near-term advantages, what we call NISQ solutions, for noisy intermediate-scale quantum.
Okay, NISQ.
In certain fields like optimization, even a noisy quantum computer can outperform a classical one for specific tasks. The risk is, of course, that if they fast-track an architecture that later turns out to be unscalable, they've wasted a ton of capital.
A very expensive dead end.
A very expensive dead end. But the pressure from global competition, It suggests they believe the first economic block to deliver something reliable for enterprise use gains an insurmountable advantage. Even if it's not perfectly fault-tolerant yet, they're betting on rapid iteration.
It's a very industrialized approach to innovation, isn't it?
It is.
They see the exponential potential, and they're using political will and targeted funding to basically force the technology out of the lab and into the messy, demanding world of business faster than anyone else.
And that focus on rapid market entry, it also implies a very aggressive stance on global IP. Every step of this fast-track journey, from a new hardware design to a unique algorithm, will be immediately locked down as proprietary intellectual property, a foundational asset for their economies.
Okay, so let's move from the what and the why to the how. The source highlights that this partnership involves specific funding to accelerate the development of products.
Right. Products, not just research.
Which confirms the goal isn't just basic science, it's delivery. This sounds a lot like a massive government-backed venture capital fund.
That specificity is everything. Targeted funding means the money isn't just spread thinly across hundreds of academic projects that might not go anywhere.
Right.
It's flowing to engineering teams that are focused on solving specific, persistent product hurdles. Like, how do we shrink the cryogenic system? Or how do we develop a standard software library for this use case? It forces the researchers to start thinking like product managers.
To ask, how can a customer use this today?
Exactly. And their roadmap is defined by 3 explicit product categories. These 3 areas, computing, sensing, and timing, these are the near-term deliverables. This is where we need to dive deep, because these 3 pillars are what define the future quantum ecosystem they want to build and dominate.
Okay, let's break them down then. Let's start with number 1, computing. This is the one we're all most familiar with. Developing the quantum supercomputers themselves for commercial use. What specific business demands are driving this?
We're seeing huge demand from fields that are just incredibly computationally intensive. Take financial services, for one.
Okay.
Quantum computing promises these massive breakthroughs in things like portfolio optimization and risk management. Your classical systems, they just struggle to model how thousands of variables all interact at the same time.
It's too complex.
It's too complex. But quantum optimization algorithms, like QAOA, they're being specifically targeted by this funding to provide real-time risk calculations. That could give a bank or a hedge fund a decisive edge in a chaotic market. The entire financial industry runs on milliseconds. Exponential speed it's gold.
So an immediate user would be a big financial institution looking to run, complex Monte Carlo simulation in hours instead of weeks. That would radically change how they respond to the market.
Precisely. And another huge area is logistics and manufacturing.
Supply chains.
Exactly. Think about a global shipping giant or a major car manufacturer. Their supply chains, their factory floor scheduling, it's all notoriously complex. Optimizing truck routes, minimizing warehouse energy use, finding the perfect assembly sequence. These are enormous calculation problems.
The traveling salesman on steroids.
On steroids, yes. A quantum computer could run these optimizations continuously, giving them dynamic, real-time adjustments that save millions in fuel and time and inventory. The source's focus on enterprise application means they're prioritizing architectures, whether it's superconducting qubits or ion traps, that have the clearest path to solving these specific, massive optimization problems first.
That makes the benefit very tangible. Efficiency equals profitability. But you mentioned different architectures there. Is the alliance just betting on one type of qubit?
That's part of the complexity of pooling their resources. They're likely pursuing what's called a heterogeneous approach at first.
Meaning?
Different research centers specialize in different things. For instance, superconducting circuits, like what Google and IBM use. They're really fast, but they're also prone to errors. Ion traps, which firms like IonQ use, are generally slower, but have much higher fidelity. They're more accurate.
A trade-off.
It's a trade-off. So the specific funding is probably aimed at integrating the best of both worlds. Maybe creating quantum networks that let these different systems talk to each other, giving you maximum flexibility for different kinds of commercial problems. They're investing heavily in that interface layer that makes these complex machines work like one single user-friendly resource.
Okay, so that's computing. Let's move beyond just processing power and talk about the second product area, sensing.
Right.
This is often the quiet but equally revolutionary side of quantum tech. Explain what sensing means here and how it moves the conversation beyond just computation.
Quantum sensing uses the fundamental quantum properties of matter, like the spin of a single electron or the the interference pattern of cold atoms to measure physical quantities with the sensitivity that is. I mean, it borders on science fiction.
Unprecedented precision.
That's the goal. Because classical sensors are always limited by noise, thermal noise, quantum sensors can break through that limit.
So how does that translate to a commercial product? Give me an example of that dramatic improvement in precision.
Okay, let's take infrastructure and resource mapping.
Right.
Right now, if you want to find underground pipes or cables or mineral deposits, you have to dig. It's disruptive, it's time-consuming. Quantum gravity sensors, which are based on cold atom interferometry, can measure tiny, tiny variations in the Earth's gravitational field caused by things underground.
So you could map out a construction site without digging a single hole.
A construction crew could use a quantum sensor to map all the hidden utilities, all the geological hazards with centimeter accuracy, non-invasively. It eliminates costly digging and minimizes the risk of, hitting a gas line.
It's basically like seeing through the ground using tiny changes in gravity. That is a massive shift for civil engineering.
It is. And another huge application is in medical diagnostics.
How so?
Researchers are developing quantum sensors, often based on these tiny defects in diamonds, that can detect the extremely weak magnetic fields generated by the human brain or the heart.
Wow.
These sensors are orders of magnitude more sensitive than current tech. That could potentially allow doctors to detect the earliest, faintest signs of neurological disorders, like Alzheimer's or epilepsy, long before our current imaging can see anything. It opens up whole new avenues for preventative medicine.
And a third example of this precision.
Autonomous navigation and defense. Quantum gyroscopes and accelerometers, they're based on sensing the movement of atoms. They don't rely on external signals like GPS.
Which can be jammed.
Exactly, jammed or spoofed. So for an autonomous vehicle, a logistics drone, or a critical military asset, these sensors can maintain ultra-precise positioning and orientation data forever, even if you're in a deep tunnel or a dense city where GPS doesn't work. The Alliance is clearly prioritizing making these sensors smaller and more rugged, getting them out of the lab and into the field.
This really blows open the scope of the Alliance. They're not just building the computers, they're building the tools to measure the world more accurately than we ever have before.
Which brings us to the third pillar, timing. A lot of people might overlook timing, but it's foundational. The focus on timing is all about highly accurate clocks and synchronization, and this is critical for economic competitiveness.
I think we all just take our timing infrastructure for granted because, it works so well. It's mostly atomic clocks and GPS signals. But if the goal is global tech dominance and ultra-fast transactions, then timing precision is the ultimate bottleneck.
It is. Our whole modern infrastructure depends on precise synchronization. And while our current atomic clocks are amazing, quantum clocks, often based on optical lattices, can achieve a stability that's up to 100 times better than the current best standards.
100 times better.
They could run for billions of years without gaining or losing a single second.
Okay, so where is that level of precision needed most urgently in business?
Let's start with telecommunications. The move to 5G and eventually 6G requires hyper-precise sync across these massive distributed networks to manage all that data. Any tiny drift in timing introduces errors and latency. Ultra-stable quantum timing products mean higher capacity and better reliability.
And you mentioned financial trading before. That whole sector runs on fractions of a second.
It's absolutely essential there. High-frequency trading firms have to make sure that trades happening on different continents are time-stamped identically. A microsecond discrepancy can be exploited, or it can lead to regulatory chaos. Quantum timing ensures that synchronization across all platforms, which is crucial for market integrity.
But I'm guessing the most critical application is probably under what they call P&T systems.
Yeah.
Positioning, navigation, and timing.
Yes. Our entire civilization runs on PNT, and most of that runs on vulnerable GPS signals from satellites. They can be jammed, they can be hit by solar flares, they can be hacked.
Right.
Ultra-precise quantum timing products can be deployed as ground-based PNT infrastructure. They can act as highly resilient backups. That dramatically improves the integrity of both civilian and military navigation. The UK and Germany, they recognize that selling the timing infrastructure that enables this kind of resilience is a massive strategic market opportunity.
So when you look at all three, computing, sensing, and timing together, the Alliance is taking this truly holistic approach. They're not just building the CPU, they're building the high-precision input devices and the ultra-stable foundation you need to make the whole quantum ecosystem actually work commercially.
It's the smart play. I mean, success in just one area, say building a powerful quantum computer, would be kind of meaningless if you couldn't also control the IP for the sensing and timing tech you need to operate it. Their investment strategy is clearly designed for vertical integration and ecosystem control.
Okay, so let's zoom out now to the global competitive landscape. The source it's really unambiguous here. It says this partnership is positioning the UK and Germany at the forefront of this cutting-edge technology. That is a definitive statement of intent.
It is. It's a declaration that, national silos just aren't good enough anymore for technologies of this complexity. The financial burden, the technological burden of getting to fault-tolerant quantum computing is so immense. It spans everything from hardware to algorithms. Very few single nations have the comprehensive resources and talent pool to lead that charge on their own. This positioning is about them aiming to define the technical specs for quantum worldwide.
And the success of that forefront position really depends on their ability to conquer what the source calls the most challenging technological hurdles of our time. And it highlights the need for a shared vision and resources to do that.
Why is international scale suddenly a prerequisite for success here?
It's because of the multidisciplinary depth you need.
Right.
I mean, the team building the vacuum system for an ion-trapped computer is using completely different engineering skills than the team writing the algorithms for financial risk modeling.
Totally different worlds. And trying to be world-class in all of those fields at once within a single national program, it just leads to fragmentation. Your resources get diluted. By merging the best minds and the best facilities, like pairing UK expertise in photonics with German expertise in superconducting fabrication, they can bypass all those redundancies and, accelerate the breakthroughs.
So a shared vision gets rid of that internal competition and makes sure that a breakthrough in one country's lab is immediately integrated into the other country's product pipeline. It's an efficiency move born from necessity.
Absolutely. And you can look at historical international collaborations for a model, things like CERN or even Airbus in the industrial sector. They proved that pooling national might can overcome these massive scale challenges and lead to global dominance even when there are political differences. This quantum alliance feels like it's applying that same blueprint to a 21st century foundational technology.
And this is where it gets really interesting for the future. The alliance's potential to set a precedent. The source claims that this kind of international cooperation could set a precedent for future tech partnerships. That suggests this UK-Germany model could be pioneering a whole new way of doing R&D.
It really does suggest a profound shift. For decades, highly sensitive tech, anything with potential dual-use applications was developed behind national walls, driven by security concerns, competitive advantage.
Yeah.
This alliance, which is so focused on rapid, aggressive commercialization, it signals a willingness to set aside that purely nationalistic competition, to go for collective technological dominance on the global stage instead.
So what does that suggest for future R&D models? I mean, if this works, it basically proves that these transnational strategic alliances focused on specific commercial goals are the only way to win in megatech, whether it's quantum, advanced materials, maybe nuclear fusion down the line.
It forces other nations to ask a really tough question. Is it better to compete fiercely and risk coming in second, or collaborate strategically and aim to be first together?
And the answer seems obvious if this works.
If the UK and Germany deliver robust, reliable products in computing, sensing, and timing in the next, say, 3 to 5 years, it provides undeniable economic proof that the collaborative model is superior for these extreme tech hurdles. It fundamentally changes the global tech race from a series of isolated national sprints into a coordinated multinational relay race.
We could see other alliances emerge.
You might see Japan and South Korea coordinating on AI hardware, or smaller EU nations pooling resources for chip fabrication. This alliance provides the template.
And that, of course, leads to the conclusion that the world watches this alliance unfold. Why would other nations, other economic blocs, view this alliance as the benchmark? What are they specifically watching for?
They're watching for two crucial things. First, the speed and the quality of the deliverables.
The result.
The results. Rivals like the US and China are tracking the technical metrics. How fast can they scale their qubit count? What's their error rate? How quickly do their quantum sensors go from a prototype to a mass-produced unit? If the UK-German team shows faster progress because of their integration, their rivals will be forced to rethink their own national-only strategies.
And the second thing they're watching
Is the governance model. How do two sovereign nations actually manage this delicate fusion of national IP and strategic funding?
The politics of it.
Exactly. The source noted the challenge of political friction. Other blocs are watching intensely to see how they navigate the bureaucracy of cross-border IP sharing, of standardization disputes, of funding fights. If they can streamline that process and prove the governance model works, it creates a viable template for others.
And it fails.
If the partnership gets bogged down in political infighting, it just reinforces the belief that purely national approaches, while slower, are ultimately safer. It is a very high-stakes stress test for the future of allied technological development.
It really seems this alliance is built less on just shared scientific dreams and more on a cold, pragmatic assessment of what it takes to win the global quantum race. We have covered a huge amount of ground on this landmark alliance, from the high-level politics all the way down to the specific product roadmaps. I think it's worth summarizing the core learning here.
The foundation, really, is that political and strategic commitment between the UK and Germany. It affirms that quantum commercialization is now a foundational economic goal. The mission is to rapidly bridge that gap between fragile quantum science and profitable enterprise use, specifically targeting fault tolerance and scalability.
And their delivery strategy is holistic. It's backed by that specific funding, and it's aimed at dominating 3 integrated product pillars. Exponential computing for those huge optimization problems in finance and logistics.
Unprecedented precision and sensing for medical and infrastructure applications.
And ultra-stable timing to secure our critical navigation and communication systems globally.
This development really does promise to reshape the technological landscape. It's going to force rapid evolution in enterprise applications all over the world. If your business relies on optimization or materials science or high-precision measurement, the success or failure of this alliance is going to dictate the technological limits of your industry for the next decade.
And that brings us back to that question of precedent. We saw why they had to pool their resources. The sheer overwhelming difficulty of the quantum challenge basically required them to unite. So we'll end with this final provocative thought for you to carry forward. We know that complex scientific problems increasingly require global cooperation. So what happens to the pace of technological innovation when national interests, driven by security concerns or trade disputes, start to clash directly with this fundamental need for global scientific collaboration?
It's a great question. Does the nature of the challenge itself force us to create new, stronger political structures for cooperation? Or will the pressure of competition eventually fragment these alliances, forcing everyone onto a slower, less efficient path? The performance of this UK-Germany partnership, especially in the face of that inevitable political friction, will probably give us the answer. And it will determine whether the 2030s are dominated by shared innovation or by competitive delays.
An excellent point that just underscores the complexity of all this. Thank you for joining us for this deep dive into the commercialization of the quantum leap. We will be tracking this alliance very closely.